Let's now take a look at this very special and famous linear recurrence relation. F sub n is equal to f sub n minus 1 plus f sub n minus 2, where the 0th term of the sequence is 0 and the first term of the sequence is 1. This is, of course, the Fibonacci sequence. And so this is an example of a linear second order linear recurrence relation. And it's actually homogeneous, and so we can use the techniques that we've learned in order to directly solve for f sub n. So f sub n minus f sub n minus 1 minus f sub n minus 2 equals 0. It's homogeneous. And so let's figure out the characteristic equation. The characteristic equation would be r squared minus r minus 1 equals 0. And so we need to solve for r. Now this time it doesn't factor very easily, and so we'll use the quadratic formula to solve for r. So r is equal to negative b plus or minus square root of b squared minus 4ac all divided by 2a. And so our two solutions are 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2. And the positive one, 1 plus square root of 5 over 2, is called the golden ratio. Okay, well, let's see. So this means that the nth term of the Fibonacci sequence will be some constant times the first root, 1 plus square root of 5 over 2 to the n, plus some second constant times the other root, 1 minus square root of 5 over 2 to the n. And then it's just the small matter of solving for c1 and c2. Now, to solve for those constants, we'll use the initial conditions, that if we plug in 0, we get 0, and if we plug in 1, we get 1. So f of 0 is supposed to be equal to 0. F of 1 is supposed to be equal to 1. On the right, if n equals 0, then both of these things are equal to 0, so that's just simply c1 plus c2. And then if n equals 1, we just simply get the numbers by themselves. 1 plus square root of 5 over 2 plus c sub 2 times 1 minus square root of 5 over 2. And so I now have two equations in two unknowns, and I need to solve for c1 and c2. The easiest way, in my opinion, to do this is to take the first equation and I'll solve for c2. So c2 works out to be negative c1 because 0 is equal to the sum of these two. Then plugging into the bottom equation, we get this is equal to c1 plus c1 square root of 5 over 2. Then we have minus c1 minus c1 square root of 5 over 2 because c2 is equal to negative c1. So we have, sorry, let's see, I did something incorrect here. Yeah, no, that's fine because I'm replacing c2 by negative c1. This negative comes out here and c1 goes inside. So this is equal to all over 2. The c1s here cancel, and then I have c1 minus a minus c1 here, so I have 2 c1 times square root of 5. So therefore, c1 times the square root of 5 is equal to 1, which means c1 is equal to 1 over the square root of 5. And therefore, by this, we know that c2 is equal to negative 1 over the square root of 5. Okay, so then that's it. I found my c1 and c2, and so I plug back into my general solution up here, and so I conclude that f sub n is equal to 1 over the square root of 5 times 1 plus the square root of 5 over 2 to the n minus 1 over square root of 5 times 1 minus the square root of 5 over 2 to the n. And that is our formula for the nth term of the Fibonacci sequence. Now, it's a miracle, almost, that whenever you plug in a number, all the square root of 5s go away. The right-hand side here always turns out to be an integer, even though we have all these square root of 5s floating around. So, no matter what, if I plug in, say, 30 and figure this out, plug in 30 here and figure this out, the decimal point always goes away, or the decimal part always goes away, and the right-hand side always turns out to be an integer. So even though it's ugly, the right-hand side is always an integer and is the nth term of the Fibonacci sequence.